So, good morning and welcome. So, let us do a quick recap of what we did yesterday. So, we were looking at the negative feedback loop whose basic block diagram was something like this. So, this is called the forward amplifier. And this is the feedback block. This is VE, the error, and this also sometimes called A is also called sometimes called the error amplifier for obvious reasons. The closed loop gain is V out by V in is 1 over f times A f over 1 plus A f, okay. And this A f is called the loop gain, and as and basically this is telling you that as the loop gain tends to infinity, the closed loop gain is simply dependent on the feedback block. The actual value of the loop gain does not really matter as long as it's so large that this AF by AF plus 1 is infinite, is close to 1. And how do we figure out what the loop gain is? Well, you break the loop. You break the loop. Let's see. Yeah, you break the loop, and you yank one side of the loop up, and then see what comes back on the other side, and what comes back must be the negative of what you put in, and the ratio of the magnitude of what you put in to what comes back is the loop gain, and it's called so because you break the loop and find the gain of the loop, right. And since if the loop gain is sufficiently large, you can realize arbitrary input output gains by simply changing the feedback the feedback block. So, what somebody figured out was to basically say that, well, if I sell this as a standalone part, then users can simply put whatever feedback network they want around this high gain amplifier, forward amplifier, and generate different input output blocks. So, the first one we saw yesterday was the non-inverting amplifier. So, this generic high gain forward amplifier, which takes the difference between two voltages and multiplies it up by a very large amount, and so this behaves like a VCVS of very large gain, and this is called the operational amplifier. And with the operational amplifier as the forward amplifier, we can make a whole bunch of useful circuits, and that is why the operational amplifier is often called the operational amplifier. Is basically a VCVS with a very large DC gain, right, typically 10 power 7, 10 power to 10 power 8, right. And this gain can vary a lot, it can vary by a factor of 10, but we do not have to worry about it, because if the gain is so large, if it varies by a factor of 10, still that quantity loop gain by loop gain plus 1 is so close to 1 that it does not matter, okay. Now, and why does the gain vary over such a large range? A factor of 10 seems like a lot. The reason why it varies a lot is because the op amps are built with transistors, and transistor properties turns out depend heavily on temperature and the supply voltage and all these kinds of things. So, it is not uncommon that the gain of an amplifier could vary by of the op amp could vary by a factor of 10 over ambient conditions and supply voltage and so on. But we do not have to still worry about it, simply because if the gain is sufficiently large, the actual value of the gain does not matter. And if the op amp is enclosed inside a negative feedback loop, right, what did we say? Well, two conditions are satisfied. One is if the op amp is ideal, therefore the input current flowing into the terminals of the op amp is 0, and the voltage difference between the two input terminals is also 0, that is by virtue of negative feedback, right. So, this basically tells us how to analyze circuits with ideal op amps. So, one is let us call this node A and node B. V A minus V B is equal to 0, and if this current is I A and this current is I B, I A equals I B equal to 0. So, therefore, the two input terminals of the op amp form a what is called a virtual short, all right, but it is important that this can only be applied in cases where there is negative feedback around the op amp. You cannot operate an op amp open loop and expect this to hold. Is that clear? With this in mind, then we started building circuits. The first was the voltage controlled voltage source with a gain K, or in general is also commonly called the non-inverting amplifier. If this is R1, this is R2, and this is V in, this is V out. What is the gain? V out by V in is nothing but 1 plus R2 by R. The next circuit that we saw in the previous lecture, we derived this from first principles, and so did we derive the transimpedance amplifier. This was I, this is R, and this is basically V out. What is V out by I? What is V out by I? It is R, right. So, this is this is a so this basically is a voltage controlled voltage source with a gain of 1 plus R2 by R1. This is a what kind of control source is this? Current controlled voltage source with gain with transimpedance all right. And so, by the way, what are the properties of an ideal voltage controlled voltage source? Let us recall what comment can we make about the input impedance? So, ideal VCVS must have these properties. Input impedances must be the input impedance of an ideal voltage controlled voltage source must be, is it 0 or is it infinite? Input impedance infinite. Why? Yeah. So, basically when you have any voltage controlled source, you are basically controlling something based on the voltage you measure with this control source, voltage control source. So, when you measure something, you should not disturb the measurement. So, that is only possible when the input impedance of the input resistance of the voltage controlled voltage source must be infinite, so that it does not draw any current and thereby disturb the voltage it is trying to measure, correct. So, Rn must be infinite. What about R out? It is a voltage source. So, basically you must the voltage source must not change when you change the load across it. So, the output impedance must be 0, all right. Now, let us see if our voltage controlled voltage source indeed has these desirable properties. So, this is our VCVS. So, how do you find the input impedance? Let us say you are given a box and you are given 2 terminals. Here the other terminal is ground obviously, right, and likewise here you are given a box with 2 input terminals, 2 output terminals, and you are asked to find the input resistance. What will you do? How will we figure this out? You apply a voltage and measure the current flowing, or you push a current, measure the voltage developed, right. So, I mean these are just 2 ways, there are any number of ways of doing this. Okay. So, if we apply a test voltage to the input, what is the current that is flowing in here? No current is flowing. Okay. So, consequently what is the resistance that we have? So, this I is 0. So, what comment can we make about Rn? Rn is infinite, all right. So, the next job is to find R out. To find R out, what will we do? Pardon? We will set the input source to 0. So, basically what we are trying to do is find the Thevenin equivalent of the network looking in here. To find the Thevenin equivalent, what will we do? We will set all the independent sources in the circuit to 0, and then we will find the resistance looking into the output port. So, again, so what do you think we can do to find the resistance looking in? Apply? Okay, apply V test. Okay, so so what happens then? Okay, one idea is to apply V test, and what happens? Okay, measure the current. So, what is the current flowing here? V test by? Why? Okay. Okay, first whenever you try to do this, you must make sure first of all that when you apply V test also there is negative feedback in the op amp, right. So, now let us say you break the loop here and you apply voltage there, and what have we done to what happens to this voltage when you increase the that voltage? What happens to this voltage? What have we done to the output? I mean, what have we put here? It will not increase because we have put a constant voltage there. So, essentially we have broken the feedback loop. You understand, right? Because whatever you do here, this is not changing because you are holding this constant using the test voltage source. Okay, all right. So, so basically there is no feedback loop when you put the test voltage source. Okay. So, in other words, another way, I mean, so what happens therefore, this voltage is 0. Okay, and remember the op amp is basically a voltage controlled voltage source. So, basically inside you have a voltage source. So, if you try to make, so you have a battery inside and you try to increase the voltage here, how much current will flow? Okay, so you have some voltage here. Then this is, say, let us say this is 1 volt for argument's sake. Now, I try to put a battery here which is 1.2 volts. How much current will flow? Infinite current will flow, correct. So, if you try to drive a voltage source with another voltage source, an infinite current will flow. So, basically if you put V test here like this, the current that flows is infinity. Okay. So, the output impedance is 0, right. Another way of doing the same thing is to say, okay, now let me, I do not want to break the feedback loop, let me try and inject a current I test and find what the voltage is, correct. So, if I inject a current I test, what comment can we make about where will all this current flow? I mean, how do we know? First check if the op amp is in negative feedback. So, we break the loop here, we yank this side up, what happens to this voltage? This is a current source, right. So, basically if you yank this voltage up, what happens to this voltage? Increase. If that goes up, what happens to that voltage? Decreases. So, is there negative feedback? Yes. If there is negative feedback, what comment can you make about that potential, the inverting terminal of the op amp? This is 0, all right. So, what is the current flowing through R1? 0. So, what is the current flowing through? So, this current is 0. So, what current current is flowing through R2? 0. So, what is the voltage at the output? 0. So, I push in a current I test, the output voltage is 0. So, what is the output resistance? 0. Where is all that current I test going? It is going into the op amp. Does it make sense? Okay, very good. So, and basically we conclude that R out is 0, all right. Yet another way of figuring out the output resistance is the following, and let me motivate that technique by showing you an example. Let us say you had a box with a battery inside and the battery had some internal resistance. So, you have these two terminals coming out, A and B. How will we find R? Short circuit and measure the current will give you what current? Vx is known, none of them is known. Okay. Okay, so basically the first experiment is to say, okay, connect a known resistor let me call this Rx. So, connect a known resistor R between terminals A and B and measure the voltage across the resistor. So, basically V1 is Vx times R by R plus Rx, okay. But Vx is unknown, Rx is unknown. How will I find, so which is known and which is unknown? V1 is known, R is known. So, this is known, but we do not know Vx. So, how will we find Rx? Current where? The current through R will be Vx, okay. So, let us measure the current, fine. So, I1 is nothing but Vx divided by R plus Rx. How will this help me? So, this is known. I mean, she's saying that the second one is the second equation. In that we don't know. I mean, you get you only get this quantity, which is but you want Rx. So, what do you think we can do? Okay. Okay, can you think of a way? I mean, so the suggestion is, why don't you use another resistor, another known resistor, and then find the voltage, and then from the two you will be able to get it. You know, what is the smarter way of doing it? Can we avoid the other resistor? Okay. The first thing is basically, I mean, without any resistor is equivalent to saying use R equal to infinity, correct. So, the open circuit voltage is simply Vx, correct, and so once you know Vx here, then you will be able to find Rx, correct. So, now let me ask you a question based on this. So, let us say we have a battery with Vx and Rx, and first I measure the open circuit voltage of the battery. So, what will I read if I put a voltmeter there? I will read Vx. Now, I connect a resistor R here, and the voltage still remains equal to Vx. Okay. Then what can we conclude? Rx is 0, alright. So, that is one more way. So, one way of figuring out whether the output impedance is 0 or not is to look at the output voltage under open circuit circumstances without a load. Then you put a load, if the voltage does not change, then it means that output resistance is 0. So, now we can apply the same idea to this circuit here. So, let us say we put some the output voltage. What is the open circuit output voltage? So, in other words, if we do not load V out with a load resistor, what is the output voltage? 1 plus R2 by R1. Now, if I put a load resistance RL, what comment can we make about the output voltage? What is the output voltage? Why is it the same? How will we go about it? I mean, we put some resistance RL between V out and ground. How will we go about it? How will we find out what the output voltage is? Exactly, same old, same old. So, basically because of negative feedback, this voltage, what is that voltage? V in. So, what is this current? V in by R1. So, what is this voltage? V in by R1 times R2, right. So, what is V out? V in V out is basically V in times 1 plus R 2 by R 1 regardless of what R L is, right. Okay, so that basically means that you change R L and there is no change in the output voltage. So, what comment can you make about the output resistance? There is no change in the output voltage when you change the load resistance. So, therefore, the output impedance must be 0. Is that clear? All right. Okay, now let us do the same exercise for this control source. So, this is a current controlled voltage source. So, an ideal current controlled voltage source input resistance must be, what must be the input resistance of an ideal current controlled voltage source? Why? Yeah. So, basically I mean you should not change, I mean an ideal current controlled source is like having an ammeter in the input circuit. So, when you put an ammeter, what is the resistance of an ideal ammeter? 0, because it should not go and change the current that is flowing in the circuit. So, basically ideally the input resistance of a current controlled whatever source must be 0. What about the output resistance of a current controlled voltage source? It must also be 0, because it is a voltage source. Okay. So, now let us see if what the actual input resistance and output resistance of this current source, current controlled voltage source are. So, so to find the current the input resistance, what do we do? Test, you can either put a test current or test voltage. So, here there is already a current source. So, we might as well use this itself. So, what is the voltage here? The voltage is 0. Does that depend on how much current you are pulling out? It does not. So, regardless of what current you push or pull from the input network from into the source, the voltage there is always 0. Is that clear? Yes. So, what is the input resistance? Input resistance is 0. All right. And now, let us say to find the output resistance, let us use what we just learned. So, we put a RL there. What is the output voltage? Output voltage is I times R. Does it depend on RL? The output V out is independent of RL. And therefore, the output resistance is